So good morning or good afternoon, everyone, depending on where you're connecting from. So today we have the pleasure to welcome Dr. Tomaso Esposti Ongaro from the National Institute of Geophysics and Volcanology in Italy. And Tomaso is located in Pisa. So today is going to talk about to us about a very complex problem, which is the multiphase flow modeling of volcanic eruptions. So thank you very much, Tomaso, and the floor is yours.
Well, thank you, Catherine, for the invitation. It's a pleasure to talk today in this environment, in this class I think it's a very good opportunity for me also to exchange information with other communities, and potentially we are always open to welcome students and undergraduate students and students in our institute. So for any question or curiosity after this talk, please contact me at the address that you find in this presentation. So today I will talk about this. As Catherine said, it's a complex it's a complex topic. It is a mixture of theoretical fluid dynamics, computational fluid dynamics, and volcanic hazards and geology. A couple of words about my institute and myself. I am a physicist as a training. I got a PhD in physical modeling for environmental protection, and during my whole career, I've been working in theoretical models based on fluid dynamics, but also in high-performance computing. We will see that to solve these complex problems in earth sciences, we need very huge and powerful computers. And I've always applied my research to volcanic hazard assessment. You might know that in Italy we have 10 active volcanoes. At the moment, we have one of the most risky volcano in the world, which is in a rest state, which it is Campi Flegrei. It is a densely inhabited area with more than 500,000 people living inside an active volcano. So this is a priority for our country to study these processes. And my institute is the Italian Institute of Geophysics and Volcanology. As a first mission, the scientific research, of course. We are all researchers, but also it has the responsibility of monitoring and surveillance of earthquakes, volcanoes, and tsunamis. So it is one of these cases where science really helps decision-making and protecting lives. And the third mission of our institute is to engage in public outreach and help people understanding natural risks. So today we focus on volcanoes, but what I'm going to show you has a broad application to many geophysical phenomena. So the technology that we develop is applied here to volcanoes, but it is also useful for landslides, for flooding, for many other geophysical processes that are not only interesting but also hazardous. So the main topic concerns complex fluids that have nonlinear rheologies and that are composed of many phases. We call they are mixture of gases, liquids, and solid particles with complex thermal effects and potentially chemical reaction and so on. And as all geophysical phenomena, they develop on a very broad range of spatial and temporal scales. And here we will focus mostly on granular flows, so flows of gas and particle and solid particles. And I will show you how these flows have a complex behavior they encompass regimes from solid to liquid to gas, depending on the concentration of the solids, but also on the stress regime they are subject to. So a bit of introduction to things that you probably know very well, but multi-phase flow really are everywhere in volcanology. So lava flows that you know are streams of molten rocks that are emitted by effusive eruption. They are made of a liquid, which is the lava, the magma without the bubbles, which is erupted from a fissure, but also has crystals inside. So it is a complex flow with a complex rheology that is strongly dependent on the temperature, but also contains solid particles, and this makes its rheology even more complicated. And another way magma is erupted is here lava fountains. This is a nice picture of a lava fountain in October 2002 at Etna. Lava fountains are the same fluid which is emitted mildly explosively and fragmented in the atmosphere. So when it is emitted, it is no longer a liquid, but it is a mixture of gas and droplets of magma. So it is a spray, basically. Modeling a spray is a complex process because these particles are interacting with each other, they collide, they melt together, and so on. And the magma itself is a complex fluid. You know, it is a polymer, basically. It's a mixture of oxides. The most important oxide is silica. Silica makes polymers with water and CO2. It can polymerize or depolymerize, changing its viscosity by orders of magnitude from a basaltic to rhyolitic magmas. So it is a very complex non-Newtonian fluid by itself. But in addition, magma contains bubbles, which are bubbles of gases that are exsolved from volatiles in the magma, and it contains crystals. So it is a complex multi-phase fluid made of a liquid, a non-Newtonian liquid, bubbles of gas, and crystals. So it is the most complex, probably, fluid that we have on Earth. Here we will focus mostly on explosive volcanic eruption. You know that magma can be erupted explosively, and it can fragment when it is erupted because of high content of gases and because of the high shear. Eventually, the magmas are erupted in the form of a mixture of gas, hot gases, and pyroclasts. Pyroclasts are nothing but particles of magma which are teared off and ejected as a mixture, as a multi-phase mixture. These explosive eruptions also form these pyroclastic flows. Not only they enter in the atmosphere, but eventually they can collapse on the flanks of the volcanoes, forming these ground-hugging currents of gas and pyroclasts that can have a very dangerous and risky impact around the volcano. So what is the basics of this explosive activity? The material is pyroclast, and these are solidified pieces of glassy magma produced by this process of fragmentation that you see here on this slide on the right. Fragmentation occurs somewhere in the volcanic conduit and transform the liquid magma with bubbles into this mixture of gas and pyroclast. I assume that you all know what is an explosive eruption, so I won't stay much in this, but I want to stress that this complex process that discriminates between an effusive and an explosive eruption is all controlled by the behavior of a multi-phase flow, which passes from a liquid with bubbles through the fragmentation level, and which transforms it in a gas with pyroclasts. And when pyroclasts are erupted, they are erupted as a polydisperse mixture, and we know that pyroclasts can have very different sizes from a few microns to centimeters or decimeters, with a broad spectrum of grain sizes. And this makes the modeling of this process extremely complex. The last but not least process that I want to mention is when this sediment, volcanic sediments, pyroclast, mixed with meteoric water, and they form this debris flow. In volcanology, they're called lahars. They are remobilized as secondary flows, and they can have a very high impact around the volcanoes. And the most infamous one was the Nevado del Ruiz event in 82. So these processes are very complex processes from a fluid dynamics point of view, but they are also very dangerous processes. So we need to model them to try to anticipate their impact. So in this seminar, I will mostly focus on granular flows, so the mixture of gases and solid particles. But the formulation is can really be applied to many multi-phase flows. So the approach I will use is a continuous fluid approach. And it is not the only approach possible. We might approach this type of flows with discrete models, so modeling each single particle or clusters of particles. This is becoming, I don't want to say possible, but affordable in some sense with modern supercomputers. But the easiest way to treat this process is to treat it as a fluid process. So with a continuous approach, we assume that the mixture of gas and particles can be treated as a fluid. And we will see in this seminar under which hypothesis this can be done. If we can treat this as a fluid, we can apply the theorems of the fluid dynamics and express the balance of mass, momentum, and energy in a controlled volume. As you can see in this picture, we have a volume that is filled by a gas and by particles of different sizes. And of course, we call these phases. These phases, the gas and the particle phases, cannot occupy the same volume. So they are characterized by a volume fraction. So every phase, which is particles of a given size or the gas, occupy a volume fraction of this control volume. And we call the volume fraction alpha, usually in the multi-phase flow literature. Alpha is the fraction of the volume which is occupied by a given phase. And using the usual law of conservation in fluid dynamics, we can write the equivalent of the Navier-Stokes equation for the multi-phase fluid, assuming that alpha is the volume fraction and the sum of all alpha is 1, because the volume is all occupied by all the phases. So for example, I've written here the continuity equation in case of multi-phase flow. You know, the continuity equation should be the partial derivative of rho over t plus the divergence of the flux of rho u is equal to 0. And this is the usual continuity equation for the Navier-Stokes equation. In multi-phase flow, we just multiply rho by alpha, and this is called the bulk density. And we can write the continuity equation, the momentum equation, and the energy equation in the same way, just by substituting the density with the bulk density. But the problem, of course, is not just the presence of all phases. We have to express the equations of state and the stress tensor for this complex fluid. And we will see that this is the really difficult part of this modeling. So before going into the equation, there are two things that I want to stress. The first, that all these phases are interacting with each other. So gas is interacting with the particles. They exchange momentum through the viscosity and the friction, let's say, and they exchange heat. So here in this slide, I introduce you to what is called the Stokes number here on the right, which is the ratio of two characteristic times. One time is tau delta, which is the typical time of our process. For example, if we are working with turbulence, is the typical time scale of the eddies of the turbulence. If we are working with an explosive eruption, it can be probably the time of the decompression of the mixture in the atmosphere is the typical time of our process. And tau v is the time a particle needs to equilibrate to the gas flow. And this equilibrium occurs through viscosity. And with a simple model that here I represent in the box, we can write this equilibration as an ordinary differential equation. And we see that this is called the Stokes regime. And we see that we can express this equilibration time as a function of the particle density, diameter, the gas viscosity, and the Reynolds number, which expresses the degree of turbulence in the flow. And we see that the equilibrium time increases with the particle density and with the particle diameter to the square. So coarse particle, for coarse particle, the equilibrium time is larger than for fine particle. This is quite intuitive. And this Stokes number is small for large. No, okay, here it is the contrary. It should be the inverse of this. The Stokes number is very small for fine particles, and it is large for large particles. Okay, and this is one of the parameters that matters for multiphase flow. The other, okay, this is the equilibrium time, characteristic time for typical pyroclastic particles. You see it for 32 microns. The typical time needed to equilibrate is 1 millisecond. For 1.5 millimeters particle is about 1 second. So we see that there is a range of equilibrium between the gas and the particles in this mixture. The other important parameter is the particle-particle interaction time. And in physics, and in particular in the kinetic theory of the gases, this is measured by the average time particle are free to fly before collisions. And this collision time or collision length is called the mean free path. And it is the average distance a particle can fly before it collides with another particle. And we know from this kinetic theory that we can adopt a fluid approach when particles interact, have enough interaction in our typical length scale. If we denote delta as the length scale we are interested in, for example, the length scale of our numerical mesh or the length scale of the process, to adopt a fluid approach, we need that there are collisions, and so that the mean free path is much smaller than this typical length scale. But also, we need that this mean free path is much larger than the typical size of a particle. For gases, this is almost always satisfied, at least on the Earth in typical atmospheric conditions. For particles, it is a bit more tricky because we see in this table that, for example, there are regimes in pyroclastic flows where the diameter can be of several millimeters, and the mean free path can be as low as 10 to the minus 4 meters. So this condition is not always satisfied in geophysical flows, not just in pyroclastic flows. We will see that when we model volcanic flows, we have to keep always in mind that the mean free path should be smaller than the typical length scale and larger than the particle size. So let's see how to model this granular regime depending on the concentration of the particle and their mean free path. So these are the four regimes that we typically treat in multiphase flow, multiphase granular regimes. And these are ordered in with increasing alpha. Alpha, I remind you, is the particle volume concentration. So for low alpha, we can describe this granular regime as a passive transport regime. So we have particles that do not interact with each other, and so they are just transported by, for example, by the wind or by a river, but they do not interact with each other. So they are not technically a fluid because there are no interaction between the particles, so a fluid description cannot be adopted. So when the particle concentration increases, we have the so-called regime of granular gases. We will see that in this regime, we can treat the particle fluid as if it was a gas of coarse molecules, coarse and dense molecules. And we can formalize this theory in the same way as the kinetic theory of gases. And when the concentration increases, collisions become more and more important, and the mean free path of the particles becomes more and more similar and close to the dimension of the particles. And we enter in what is called the dense granular gas regime, or the collision regime, in which the collisions are dominating the dynamics, and the finite size of the particles becomes to be very important. And in even more concentrated regimes, collisions are very frequent. Particles are often in contact with each other, and so frictional forces dominate over collisions. And we enter what is called the granular liquid regime. And when particle concentration increases a lot, we have a compaction of particle, and in this sense, we do no longer talk about the fluid, but a granular solid. We won't discuss this in this seminar. So let's see the first regime, the passive transport. So we are in the condition in which particles do not interact with each other. This is the typical regime of the atmospheric transport of pyroclasts. During explosive eruption, pyroclasts are injected into the atmosphere. They can reach the stratosphere. You can see these very nice videos and picture of explosive eruption with these eye plumes. When these particles are injected in the atmosphere, they are taken by the winds and they are transported for very long ranges. A relatively small eruption can inject millions of tons of particles in the atmosphere, and these are transported for thousands of kilometers. The largest eruption can leave their particles in the atmosphere for years. So in this case, particles are just transported by the wind and they fall down eventually by gravity. So we describe the motion of each particle by Newton's laws, just describing the force that the wind exerts on the particle, which is here. You see FD is the so-called drag force. This is a simplified version of the drag force, but quite satisfactory for us. Then there is, of course, the gravity force, and there is close to the vent a force depending on the pressure gradient. And this is enough to describe our motion. And this is what we have done since, for example, in 2010 with the eruption of Eyjafjallajökull in Iceland. And of course, for this kind of modeling, the most important part is to have a good description of the wind field. So it is a coupling of the wind field and the passive transport. And of course, computationally, it is expensive because the domain is large, but the motion of the particle is really dominated by the effect of the wind. and this is possible because the concentrations here are very, very low, and the mean free path of the particles is of the order of thousands of kilometers. So a particle can travel thousands of kilometers before encountering another particle. When we increase the particle concentration, we enter what is called the kinetic regime, so what I've called the granular gas regime. And this is the process of formulating the fluid dynamics of these granular gases is interesting because it assumes that even for a particle flow, particle collision are frequent enough to establish what is called the local equilibrium kinetic distribution, what is called the Maxwellian distribution. There is a correction because, of course, collisions, particles differ from molecular gases because their collisions are not elastic. Collisions between among the molecules in a gas are they conserve both momentum and energy, whereas collision between solid particles are non-conservative. They do not conserve energy. But we assume that the Maxwellian distribution is reached eventually in this form. I hope you are aware of this distribution function. Is a Gaussian distribution of the velocities. This expresses the deviation of the velocity of the single particle with respect to the mean velocity, which is capital U. V is the instantaneous velocity of each particle. U is the average velocity. And to express this Maxwellian kinetic distribution, we introduce something which resembles the temperature of a gas, but here it is called the granular temperature, which is the root mean square of the fluctuating velocity. So the deviation of the instantaneous velocity from the mean velocity. And this is exactly introduced as the temperature in a gas, with the difference that whereas we have thermometers to measure the temperature, we don't have a tool to measure the granular temperature. But the temperature, again, measures the fluctuation of the velocity of the particle. And in the same way, with the same formulas, we introduce an equation of state for granular pressure, which, analogously to molecular gases, is proportional to the granular temperature. And with these ingredients, we can write the equations for the granular gases and an equation for the stress tensor. And at the first order, the stress tensor is, as in molecular gases, is Newtonian. The stress tensor is proportional to the strain rate of the fluid, and the viscosity coefficient, as in the gas, is proportional to the temperature, to the square root of the temperature. Of course, we will need an equation for the transport of granular temperature, which accounts for the production of granular temperature, diffusion, dissipation, and damping. I won't enter these technicalities. These are the equations that come out. These look complex, but these are simply the Navier-Stokes equations in which we have introduced the volume fraction for each particles every time there is a density. We have added the drag force between the gas and the particles, and we have this stress tensor, which is a Newtonian stress tensor, which is expressed as a function of the granular temperature. So formally, there is no difficulty in this formulation. It is just a bit tricky, just to be careful with the index. And of course, the closure equation depends on the type of particles. There are regimes in which we can simplify a bit these equations. For example, when the particles are fine enough, and the volcanic plumes are quite good for this kind of approximation. And here I mention a paper that we published almost 10 years ago about the modeling of volcanic plumes with this formulation. And in this case, we can simplify a bit this system of equation and just collapse the different equation of each phase into a single equation with some correction due to the non-equilibrium between the gas and the particle. And this is the application that we did to an eruption that occurred 10 years ago in Camp Bucco. You see that what you see in the isosurface is the concentration of the particle. Here, the particles are assumed to be quasi-coupled to the gas in the isosurface, but the coarsest particle, you see, they start to fall down because of the gravity and because they are not perfectly coupled to the gas. Okay, this is a simulation. We developed this numerical code. It is based on OpenFOAM, which is an open source tool for computational fluid dynamics. In our group, we have a team that develops solvers in OpenFOAM for volcanic applications. If you are interested, you are welcome to write to us for more information. So what happens when we increase more the concentration of the particles? Of course, things become more complex because collisions become important. And as I said, the collisions are not conservative, so they dissipate energy. So eventually, every granular regime ends with particles if it is not supported by an injection of energy, particles eventually fall down and sediment. And this is the fate of every particle on Earth, let's say. So I won't go into the details of the formulation because it is formally a bit more difficult. I just tell you what happens when we increase the particles. So when we increase the concentration of particles, the volume of the constituents becomes important because their size becomes comparable with the mean free path. So this implies that there are corrections to be done to the pressure that this particle feels, and this is the correction that is, so the first term, rho theta, is the equation of state in the kinetic regime, in which the pressure is proportional to the granular temperature, and we have this correction that is introduced in the collisional regime, in which this term 1 plus E accounts for the non-elastic collisions, is a factor that depends on the elasticity of the particles. G0 depends on the correlation function between the particles, which is proportional to their size, and alpha is the particle volumetric fraction. So there is just a correction of the pressure, and in the same way there is a correction to the viscosity. It is more complex. It depends on the correlation function and also on the strain rate. So the stress tensor becomes non-Newtonian. But the machinery, let's say, is more or less the same. Of course, we cannot solve this kind of complex models analytically. So what we do is to develop numerical models with all this physics inside, and then we try to solve this numerically. So in the last years, with a colleague, Mattia De Micheli Vitturi, we have developed this new numerical solver based on OpenFOAM. It is called OpenPDAC. It describes the full physics of the multi-phase gas particle flows applicable to volcanic regimes. And here I will show you an application to explosive phreatic explosions. Phreatic explosions are a type of eruptions that are not triggered by new magma coming to the surface. They are just instabilities of the shallow hydrothermal system of a volcano. So we have a volcano that has an active magmatic system, and this magmatic system provides gas and heat to a fumarolic system. And eventually this shallow hydrothermal system can be destabilized by an excessive flux of gas and heat. And when it increases its pressure, it increases its temperature and eventually explodes. And this is something that has happened recently. This picture is the phreatic explosion in Whakaari in New Zealand in 2019. More than 50 people died in this in this eruption, and this is also the risk that we are currently facing both in Campi Flegrei in Italy and in Vulcano. So the need to model this kind of process derives from the need of understanding the dynamics and trying to anticipate the impact of this eruption. So this is a sketch of the mechanism. So there is a reservoir of gas and particle, which is eventually at high pressure and temperature, and at time zero, we let it explode. So the initial concentration is very high of particle. So we have to describe a process that goes from a very dense concentration to dispersal of the particles in the atmosphere and eventually formation of pyroclastic density current. So again, increase of particle volume fraction and change of regime. This is why we need a numerical model that encompasses all these regimes. And we solved this numerically. So we build a numerical mesh around our volcano. This is a crater. This is the volume where we put our multiphase mixture at high pressure and high temperature. We use a digital surface model to construct this numerical grid. And these are the results. After 2 seconds that we release this mixture, you see here there are isosurface of the fine particles that are more coupled to the gas, and you see here the dots are the coarsest particles that are not coupled not tightly coupled to the gas, and they form this kind of ballistic shower which forms already at 2 seconds. And this is 5 seconds. Sorry, there is not a scale. So this is about, this is 50 meters. So this might be about 200 meters or 500 meters. And this is after 10 seconds, you see that ballistics are ejected while this small plume forms. And this is the 3D results. This is the 3D result after 1 minute. And you see that pyroclastic flows are formed. And here you see there is the village. This is the island of Vulcano in the Aeolian archipelago. And this is a simulation of a small phreatic explosion close to the beach. This is the animation of another simulation, in this case from the crater center. Of course, it is a scenario. It is not something which is based on measurements. It is something that we do to anticipate potential effects of this kind of eruption in the future. So you see that after ejection, there is formation of pyroclastic flows. The colors here represent the temperature. Of course, there is also thermal exchange between the particles and the gases. And you see that while the time proceeds, the color becomes more blue because the temperature decreases with the mixing with the atmosphere. But at the base of the pyroclastic currents, where particles are more concentrated, remain hot. Okay, this is just to mention the computational effort that we have to face. This simulation has been performed on the European LUMI supercomputer in Finland. And we have done this in the framework of what we call the Center of Excellence for Exascaling Solid Earth. It is a European project that is aimed at developing these high-performance computing facilities and software for volcanic simulations and not only, also for earthquakes and tsunamis. For this simulation, we have used 5 to 8 millions of cells, and every scenario of this, every simulation took 12 hours on 500 CPUs. 500 processors, which is equivalent to running for 3,000 days on a single laptop, let's say. So, of course, we cannot afford this kind of complex simulation with a normal computer. We can do something smaller, but sometimes it is not enough to simulate a volcanic eruption, because volcanic eruption originate on very small scale on a volcanic crater, which is in this case the diameter was about 10 meters, but then they develop over kilometers. So the number, it is called a multi-scale process, and the number of degrees of freedom increases rapidly and goes beyond the capability of a single computer. So for the reason we say that the HPC, the high performance computing, has really changed the perspective also for addressing uncertainty quantification in volcanic processes, because the initial parameters for this simulation are characterized by high uncertainty, and to give a satisfactory response, we have to simulate many scenarios, tens or hundreds of thousands of scenarios, and we can do this just using high-performance computing. Okay, in the last 5 minutes, I would like to talk about the liquid regime of granular flows. In this case, I leave behind the kinetic theory of granular materials, because when we go into the frictional regime, when particles are really in contact with each other, the problem is that we lack a satisfactory microscopic model. And so most of the models are empirical ones, and they are usually derived from experiments and from laboratory experiments or from numerical simulations. When the particle concentration increases, usually granular flows are treated as plastic fluids with the plastic rheology. The easiest plastic rheology is the Coulomb rheology, in which the shear stress is assumed to be proportional to the normal stress. Here in this sketch, you can understand what this means. If you have a confined granular flow, which is confined by a normal stress P, and you apply a shear stress, the system organized in such a way that the shear stress, when the flow starts to move, is proportional to the normal stress, and the factor is called mu, is a constant, and usually it is written as the tangent of delta, where delta is called the repose angle of the granular fluid. This is the simplest plasticity model. In the recent years, let's say in the last 20 years, however, this plasticity model has been modified and we call this the mu of I model. It is known as the mu of I models. And expressing this coefficient mu as no longer a constant, but as a function of this I, which is the inertial number. Inertial number is a combination of the parameters of this kind of configuration. It is written here, and the expression of the mu of I is an empirical one. There are reasons why the mu should depend on I, and this can be derived from dimensional considerations, but basically this is an empirical model, but it works quite well also for geophysical flows. And usually to apply this kind of models, we do not apply this in 3D, because the tensorial formulation of these empirical models is complex and not univocal. Usually these models are applied in depth averaged equation. So the equation that I've shown before are averaged over the vertical direction, the same direction of the gravity, assuming that geophysical flows are usually characterized by an horizontal length scale that is much greater than the vertical length scale. And in this condition, we can simplify these equations and assume that the pressure is an hydrostatic pressure, so we no longer have the equation of state for the pressure. We assume that the pressure is hydrostatic, and with this integration, the variables, and we also assume that the flow is incompressible, because in this high density regime, the variation of the density are small. And in this condition, these empirical rheological laws can be applied. So because I just have 1 minute more, I skip a bit the formulation of the equation, but you see that the variables are the thickness of the flow and the velocity of the flow, and also the temperature. And we can write this equation in a nice conservative way and solve with numerical models. And we develop these models also in INGV in Pisa. And I show you an application, a typical application again on Vulcano Island, studying these phreatic explosions. We also ask ourselves how stable is the edifice, because this might trigger phreatic explosions. And so we have modeled the instability of a part of the edifice and the formation of landslides with this kind of model. And this is the typical output of this kind of model. It is the thickness of the flow and the velocity of the flow in each point of the domain. So I go quickly through the conclusions. Granular flows, also in volcanic settings, display complex behavior, and they encompass the typical regime of solids when the concentration is high, liquids, and gases. And the specific regime depends mostly on the particle concentration, but also on the stress regime. And for dilute and intermediate regimes, we have a good theory, good microscopic theory that can help developing fluid models, and it is the kinetic theory of granular material that provides a satisfactory framework for the modeling and also for numerical simulation. For the concentrated regimes, unfortunately, a unique model based on a rigorous microscopic description is still lacking, so we usually use empirical models. An important thing to mention is that in volcanic granular flow, not only the interaction among the particles are important, as we have seen, but also an interaction with the interstitial fluid. Which can be air in explosive eruption, but also water in lahars and the different volcanic gases. It is a key dynamic factor, especially in explosive eruption, especially in those situations in which there is an explosion, the compression of the gas, which drives the entire dynamics. Some important mechanisms in these processes are still difficult to model. So I've talked about the grain size distribution, and I have always assumed that this grain size distribution is constant in time, but of course, we should learn how to model the fragmentation process, so the generation of the particles, their interaction, and eventually secondary fragmentation or even aggregation among the particles. For liquid regimes, depth average models provide a useful and effective tool for the description of shallow surface granular flows, and also for drawing maps of invasion of granular flows for hazard assessment. So, of course, the work is still always ongoing, both on the theoretical side to understand what model is working better in the condition we are working, but also to calibrate our models and to validate them against the observation. This is a complex task because, of course, observing volcanic eruption is not easy, but the interaction between observations and modeling is more and more important and a growing field of research. I thank you for your attention. I hope I was in good timing. I leave the floor for question, if any, and comments. Thank you again.
So thank you very much. Thank you very much, Tomaso, for showing us all these different regimes for volcanic granular flows. So the floor is open for questions. So you can either unmute yourself and ask your question or put your question in the chat. Would you like me to start? So I create some momentum of questions. So maybe I can ask a very simple one. You showed a simulation. Was it real time, this simulation you showed? Because it was 120 seconds or something? Or
I don't know if the first one or the second one. This one or the...
Yeah, this one. I was wondering if it was real time or not.
It's a bit accelerated, I would say.
Yeah.
But you have the time here. So after 20 seconds, you have this formation of the explosive plume and starting creating pyroclastic flows after about 30 seconds, and after 1 minute, you have invasion of the foots of the volcano. So this is the typical timing of this phenomena. So if you
So
videos online of this Vakari eruption, it is impressive how fast it goes.
Yeah, so you have no reaction time for
There's no
people
reaction
living.
time. So the purpose of this modeling is really planning. So making scenarios. So assuming that, of course, there is the need of associating then probabilities to the given scenarios, but the idea is to explore all the potential variability of the initial conditions, and then deciding based on the real-time observations. So selecting one scenario or the other based on the observations. It is not an easy task, but it is just a first step.
Yeah, but even if you make several scenarios, your time scale will not change much, right?
No, having this simulation can help planning mitigation action, in the sense that we know that some regions can be impacted by some phenomena, and of course it is a large eruption. Of course, it's not probably what we expect at Vulcano at the moment. It is just an exercise to see, but there have been eruptions of this size in the past, let's say, and volcanoes in the world show this kind of behavior. So it is important at least to be aware. Then when signs of instability occur, this is a potential outcome.
Okay, thank you. Any question, Laurent?
Yeah, I would like to ask, so you're showing some example simulations there, right? But you also mentioned like you want to change perhaps some of the starting parameters to see the variability. Can you give us an idea about how representative the specific simulation that you showed, how they are representative of the system? That is, how, the kind of range of different outcomes that you might expect in any of the examples that you showed.
Of course. No, this is, of course, the most important aspect of using models, because what we do is to try to reduce the number of parameters, of course. So these kind of models have many parameters, which are both on the microscopic scale, and for constraining this, we use laboratory experiments at a small scale. But then, of course, we have to decide the mass eruption rate, the initial pressure, the initial temperature, and these are typical volcanological parameters. And the uncertainty on these parameters is the largest one. It's called the epistemic uncertainty. We don't have constraint, so we explore the whole range. The variability can be large. We use comparison with past eruption to validate the model. In this case, for example, this was the Calbuco event. So we learned how to constrain the initial parameter to fit some observations. For example, the height of the plume, the size of the umbrella, and so on. When we use this for hazards, of course, we don't have any way to constrain initially the mass eruption rate. So we make scenarios. We say, okay, let's make a small, a medium, and a large. And from our experience, we know that small means in this range of mass eruption rates, medium, but then choosing between these scenarios is not always possible because, for example, for phreatic explosions, we don't know yet how to correlate the energy of the explosion to, for example, the deformation of the ground before the eruption. And this is ongoing research. It is the coupling of many different systems is needed. Also, we still don't know how to reconstruct the pressure in the hydrothermal system before a phreatic explosion. So, of course, this is just a piece of the puzzle, and we need to work to integrate in a real forecasting system.
But I guess I'm more curious about the outcome of the simulations. Like you showed an example, I think it's the island Volcano, where you have that town that gets, you know, covered at some point. Is that happening in every simulation, or is there some cases where the plume goes in the other directions? And
yes, of course.
are you reaching the stage you can make statistics on that to really try to plan which region?
We are aiming at making some statistics in this. Of course, we needed this high performance computing because if we have to make statistics, we have to run this scenario hundreds of times. And for the moment, we have assumed that all the scenarios are the same probability to make statistics. And we say, okay, let's see how many produce pyroclastic flows, how many do not. And we just weight the impact with what we obtain. And of course, if we increase the energy, the conditions go towards more convective conditions, and there is no pyroclastic flow, but there are ballistics anyway, so we can make a statistics of the ballistic impacts. This is something that is feasible. I don't have in this presentation, but eventually, if you are interested, I can send you some information about that.
Thank you.
You're welcome.
Any other question? No question from our student?
I leave my email if any question
Yes.
comes out. I'm welcome. I am happy to respond.
Okay, so maybe we will close it there. And thank you again, Tomaso, for giving us this great presentation. Thank you very much. Thank you.
Thanks to you for the invitation, and good luck for your school. And we are always open for connections. Thank you.
Okay, we will connect. Ah, you have a comment. Thank you from Alberto.
Ah, Alberto. Hi, Alberto.
Ciao, Tomaso.
Ciao.
Okay, so have a good evening or good day for everyone. Thank you.
Thank you again.